Alrighty, so 9.3 is all about the three-dimensional coordinate system because ultimately our goal is to talk about three-dimensional vectors, so I suppose 9.3 wanted to take a quick break and breather from it, from vectors, just to get our feet wet with three dimensions. Um, and it turns out that without getting too in depth about the visuals behind it, because it's quite difficult without a computer to draw three-dimensional figures, we'll find that the background mathematics behind it, the algebra, the arithmetic, are pretty much similar, pretty much the same. So by the end of today, we should be able to find distances between 2 points in 3 space, find equations of spheres, and find this thing called a trace of a sphere. And I did say that a lot of the mathematics behind three-dimensional systems are similar or built upon the mathematics of two-dimensional systems. To prove my point, let's sort of make a comparison table here. So we'll make a two-column table, like basically split the half the page in half. One half will be the two-dimensional system that you're more familiar with, and the other half will be the three-dimensional system, which we, technically uh, do not know. Two dimensions. So what are some obvious facts or some equations formulas that we know in 2 dimensions? Well, looking at our lesson goal, the first thing we need to talk about is the distance between 2 points. So in 2 dimensions, we know that the distance between point P, which in a Cartesian system is some x comma 1, y comma 1, and point Q is x comma 2 comma y comma 2, is, this is the distance formula, it's just Pythagoras' theorem. It's the differences in x squared plus the differences in y squared. And now, what comes first, the x sub 1 or the x sub 2, it technically really doesn't matter since we're squaring it, but just to make things consistent, it's always final minus initial. Well, guess what? It turns out that if I want to find the distance between 2 points in 3 space, the only thing that's different between 2 space and 3 space is that 3 space has an extra dimension. So the distance between point P, x1 comma y1, but since we're in 3 dimensions, it also has a third axis, z-axis, z1, and point Q, which is x sub 2 comma y sub 2 comma z sub 2, is the differences in x squared plus the differences in y's squared, as we expect, but it also tacks on the differences in z squared. So you can see that we don't really have to augment our equations or formulas too much because it's just an extension of the Pythagorean theorem in 2 space. Now, for the sake of brevity, I'm not going to show the actual proof of the distance formula in 3 space, but if you are interested, it's a very simple diagram to take a look at. Feel free to ask me some other time. Just feel free to contact me, reach out to me, and I'll gladly show you. This looks like phi space. It should be 3 space. Right. There's some things, other facts that we should know in 2 dimensions as the equation of a circle, right? So in 2 dimensions, we have, should I put a, yeah, let's do a slash, let's continue. In 2 dimensions, we know the equation of a circle centered at some center x comma y, or h comma k. In other words, if you had a circle here, looks like a circle, sure, and you're on a coordinate system, and you have some center. Now, the letters that we typically use for the center of a circle is h comma k. We should know that a circle by definition is defined by a radius. The radius by definition is the distance from a center to a random point on the circumference. So since this is just a random point, he's going to have coordinates x, comma, y. Well, we know that the equation of this circle is always going to have this format: x minus some h squared plus y minus the sum k squared equaling r squared. That is the fancy schmancy formal definition, or the equation of a circle. Gee, I wonder how that equation changes once I take a look at the three-dimensional equivalent of a circle. Everyone should know that the 3D version of a circle is a sphere, right? A sphere is sort of like a three-dimensional circle. So, what is the equation of a sphere centered at, now since we're in 3 dimensions, it's not h comma k, because we have the coordinates. It's going to be h comma k comma l. Now, I am not an artist, so I don't know how to draw a 3-dimensional sphere really well. So we did say a sphere is just a 3-dimensional circle, so I imagine it has to start with the circle. And then to make this guy sort of look 3D, let's do like an arc here. So there's the outer edge, and then here's the edge in the back, sort of like a lens. I think that sort of, if you squint your eyes hard enough, it sort of looks like a sphere. Sure, the Eye of Sauron. So it has some center, but it's a 3-dimensional center. So it's this is h comma k comma l, and just like circles, spheres are defined by the radius, and radius by definition is the distance from the center to any of the outer edge. It doesn't have to be the circumference, because the circumference is meaningless with spheres. It's to the outer edge, and this is some random point x comma y comma z. So here's the equation of a circle. Well, the equation of the sphere should be very, very similar, except you have a z component. So not surprisingly, this is the equation of a sphere: x minus h squared plus y minus k squared, just like a circle, but you tack on the z component, z minus l squared equals r squared. Right. So yeah, when we're in 3 space, it is new, right? It's stuff that you're not really thinking about in your everyday lives, because you're typically doing Euclidean geometry, but hopefully lots of this 2-dimensional stuff that you've learned will translate to 3 dimensions. How do I find the distance between 2 points in 3 space? It's just the same distance formula that you've grown up with and learned, except you have an extra z component. How do you find the equation of a sphere? Well, since a sphere is just a 3-dimensional circle, it's the equation of a circle that you've grown up with and you've been doing over and over and over again, except you have this extra z component here, right? So I hope that is, that's sort of nice. That's good for us, because that means we don't have to reinvent the wheel. The math behind it is super duper easy, right? Suppose I ask you to find the distance between point P, say, I'm making up numbers, 2, -1, 7, tossing some negatives in there, and point Q, I don't know, 1, -3, 5, right? This should just be a straight up application of the distance formula, right? So the distance from P to Q is equal the square root, subtract the x's, and again, technically the order doesn't matter, but we always like to do final minus initial. So subtract the x's and square it, plus subtract the y's and square it, plus, this is the only difference in 3 space, you have a z component to handle. Subtract the z's and square it. So what's that going to be? That's 1 squared is 1, so that's 2, 4, that's 2, 4, that's 4, 4, 8, 9, so the whole thing is 3. So we know that the distance between these 2 points is 3 units long. Sometimes it'll be a nice clean number like this, sometimes you'll have radicals, but that should be no problem. What else? What lesson goal did we have? So that's our first lesson goal: find the distance between 2 points. Finding equations of spheres. So finding equations of spheres is very easy. We have a template for it. If you need to build an equation of a sphere, just use our template here. So suppose I ask you to find an equation of a sphere with radius 5 and center -2, 1, 3. Now this is the easiest type of question because they basically gave you everything you need. Since they gave us a radius of 5, that's clearly your R. And remember, your centers isn't an ordinary point, x comma y comma z. Your center it has special letters. This is your H, K, and L. So we have a general format, r squared equals x minus h squared plus y minus k squared plus z minus l squared. Basically, we're done. Now, this is a trivial question. What is the equation of a circle? Plug in the r. R is 5, so 5 squared is 25. Or excuse me, the equation of a sphere, 25 equals x minus h. Well, h was a -2, so that's a +2 squared plus y minus k. K was 1 squared plus z minus l. L was 3 squared. That is the equation of that sphere. All right, so that's sort of a trivial example. Let's take a look at a non-trivial example. Suppose I asked you to show that x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equals 0 is an equation of a sphere. State its center and radius. Wow. Well, how do we do this problem? Well, let's scroll up to the general statement or general format of a sphere, which I think I rewrote down here. Yeah, so here's the general structure or format of a sphere. Notice how the equations of the sphere always has one term of x being squared, one term of y being squared, and only one term of z being squared. Only one term of x, y, and z. But in this problem, we have multiple x terms. We have multiple y terms. Multiple z terms. So, and more importantly, we have multiple x terms. One is a square, one is linear, and same thing for y's and z's. So we need to somehow bring all the x's together, all the y's together, all the z together, and transform them into parentheses squared. Well, that's a classic application. It's calling out for completing the square. So that's basically it. That's the only technique or methodology thing we need to consider for these types of problems. So let's go ahead and do this. Now the first thing I'm going to do is I'm going to rewrite the equation to group all the x's together, to group all the y's and z's together. So I'm going to rewrite this problem as x squared plus 4x, and I'm going to leave a gap because I know I'm going to have to complete the square, plus y squared minus 6y. I'm going to leave a gap because I'm going to complete the square, and the z's, plus z squared plus 2z. Now when we complete the square, and leave a gap, when we complete the square, we don't want any extra constants. So I'm going to move or subtract this 6 on the other side. Now it's time to complete the square. Let's see if we can remember how to do that. Completing the square, the pattern is half the linear coefficient, then squared. So half of 4 is 2, 2 squared is 4. So to complete the square for the x, I need to add a 4. But of course, what you do to one side, you got to do to the other side. Let's move on to the y's. To complete the square, it's half the linear coefficient squared. Half of 6 is 3. 3 squared is 9. So I'm going to add 9 to both sides. And then for the z's, I'll let you think about that for a moment. Stalling some time so you guys can figure it out yourself. What magical constant would you need to add to both sides to complete the square? Hopefully everyone got a 1, plus 1 to both sides. Okay. And that's it. You're basically done because once these three groups now are factorable, right? That's why we complete the square, because we transform them into factorable trinomials. So for the x, it's always going to be x half the middle number squared, plus for the y is y half the middle number squared, and then for the z, it's going to be z half the middle number squared. And then you just go ahead and, do the math on the right-hand side. So negative 6 plus 4 plus 9 plus 1 is negative 2, negative 1, that's going to be 8. So that right there is the equation of a sphere. But we also have to state its center and radius. So just remember, the centers are the numbers that are adding and subtracting the x, y, and z. But it's always backwards. Remember, the general structure of a sphere is always minus h, minus k, minus l. So these numbers here are actually minuses. So h is not positive 2. H is actually the opposite of 2. So the center is going to be opposite negative 2, comma, opposite positive 3, comma, opposite negative 1. And then the radius, remember that the constant is always the radius squared, so the radius would have to be the square root. The square root of 8, of course, is 2 square roots of 2. Okay. So those types of problems are the easiest, I think. So the last lesson goes to find this thing called a trace. So the trace of a sphere is the equation of the circle formed by intersecting a sphere with a plane. And we mean a mathematical plane, not an airplane. That would be bad. You don't want to intersect spheres with aeroplanes. What that means or looks like is, again, I'm gonna really, this is gonna suck because I can't draw three-dimensional figures, but let's draw a three-dimensional circle or sphere again. And it's a little bulge arch. This is true with any circle, any sphere. If you were to cut this sphere anywhere, let's say I slice off the top, right? Or I slice it at an angle. Again, I can't draw this. Or if I were to slice it this way here. So imagine this was, I don't know, a scoop of ice cream, and you took a knife and then you just cut it horizontally, say this way. So this represents the horizontal cut. Right. How can I do this? I really can't. I suck at drawing. I'm not going to advocate you guys go out and grab knives and whatnot, but the next time you have an opportunity to see something circular, an orange, or if you find a well-formed grape, or if you have some modeling clay, make yourself a little ball here, and you'll find out that no matter how you slice that sphere, if you look straight dead on center at the cut, it'll always look like a circle. That's what the trace is. The trace is, imagine, let's see if I can draw this. So it'll look something like this. This is the time when I wish I was an artist, right? So isn't that sort of like an orange with its top cut off? Well, it turns out that if you look at this part right here, dead on center, it'll always be a perfect circle. And if that's true, no matter where you cut a sphere, if you look straight dead on the slice, it is a circle. And that's what we call the trace. It's sort of the circle that forms when you take a cross section of a sphere. And so when they ask you to find the trace of it, they want you to find the equation of it. And when they do this, they'll usually tell you where to slice it. So for example, for the sphere, x minus 2 squared plus y minus 4 squared plus z minus 5 squared equals 36. Describe the trace in, and this can be a two-parter, the xy plane, and B, the plane z equals 9. So how do we do letter A? Now the xy plane is your regular Cartesian plane that we think of, right? This is your xy coordinate system. But in 3 dimensions, we draw it a little bit differently. In 3 dimensions, the coordinate system sort of looks like this. If you were to look at the corner of your room, that's basically what you can look at to visualize a three-dimensional coordinate system. Now, by standard convention, you can label these however you want, but most mathematicians label the top one as z, the bottom left as x, and the one pointing to the right as y. The xy plane is the floor. If you imagine this being your room, right? So this is a wall, this is a wall, and this is your floor. I was going to put room. The xy plane is the floor. Now they give you information when they say the xy plane. If you're on the floor, you can sort of think z as height. How high off, the question is gonna sound weird because it's obvious. How high off the floor are you when you're on the floor? In other words, what is your height, z, when you're on the ground level floor of the xy plane? Hopefully this is very obvious to know that this is z equals 0. And that's all you have to do to find the trace, is just for letter A, just plug in 0 for z in the equation of a sphere, because we know that the trace of the sphere in the xy plane, z must equal 0, so that needs to be true for the equation. So x minus 2 squared plus y minus 4 squared plus plugging in 0 for the z. Now remember that the equation of a circle already has these components. That's necessary for the equation of a circle. So I'm not going to touch him. I'm going to go ahead and simplify the rest. So that's 25, because 0 minus 5 is negative 5, and when you square it's 25. And then, of course, equation of a circle, all the constants are on one side. You go ahead and subtract it to the other side. So 36 minus 25 is 11. So that is the equation of the trace of the sphere. I'm gonna be the textbook's gonna be very nitpicky, since the instructions said describe instead of find. They actually want you to describe it. So I guess I shouldn't box that. So we can say the trace is a circle centered at, and then we can read the center, positive 2, positive 4, with a radius of, well, since the equation of a circle, that's always going to be r squared. R is the square root of 11. One thing I will augment, I pulled this question. Wow, my brain froze there. I pulled this question from the textbook, is that since we're still technically in 3 dimensions, they want you to write the center as a 3-dimensional point. So how do we come up with this equation of the circle? R was 0, so you go ahead and make the R, not R, Z. Z was 0, so you go ahead and make the Z coordinate as 0. And then to do part B, I hope you guys recognize it's the same thing, but this time they explicitly tell you, hey everybody, Z is 9. So literally plug it into the same same equation, but make sure z is 9. So let's do that fairly quickly here. So for part B, x minus 2 squared plus y minus 4 squared plus plug in a 9 for the z. So that's x minus 2 squared, y minus 4 squared. So that is 9 minus 5 is 4. 4 squared is 16. And then that's going to give us a 20. X minus 2 squared plus y minus 4 squared equals 20. So now we can describe it. The trace is a circle centered at 2, 4, but the z-coordinate is now 9, with radius. Remember, this is always going to be radius squared, so the radius is the square root of that. Square root of 20 is 2 rad 5. Yep, there we go. So that's how you find the trace of a sphere. It's basically finding the equation of the circle that results from taking a sphere and slicing it up. When you slice a sphere, they'll usually tell you what the x value is, or what the y value is, or what the z value is to plug it in. So that's it. That is just a little introduction to three-dimensional systems, and I hope you guys recognize that the math, at least, although the picture is completely different, there is a big difference between a circle and a sphere, or what's a square and a cube. Those are two-dimensional, three-dimensional pairings there. Although there are significant physical differences, I hope after this lesson you'll realize, you know what, the math, they're pretty similar. So have at it and good luck.